let's talk about Schur polynomials a little bit more. So recall the definition. For lambda, a partition of D into at most n parts, the Schur polynomial was defined to be the quotient of the alternate A lambda plus delta by A delta, right? The denominator is the Van der Waals determinant. Okay, so we showed last time that this is in fact a symmetric polynomial of degree equal to mod lambda. So D in this case, it's a symmetric polynomial homogeneous of degree D. Now here's an important statement about the Schur polynomials theorem. The Schur polynomials form a Z basis. So S lambda x1, x2, xn as lambda varies over PDN is a Z basis of the space we denoted lambda ND, which is, recall, the space of symmetric polynomials of homogeneous of degree D in n variables. So I should say in n variables. Okay, so this is homogeneous symmetric polynomials. Okay, so in this sense, it is a bit like the monomial symmetric functions, which also have the same property. Okay, so let's see how one proves this. The key here is to observe that our definition of Schur polynomials is really in terms of the alternate. Okay, so we'll prove this by reducing it to a statement about the corresponding alternates. So here's a proof. So recall we had shown the following when we talked about alternates. Okay, so recall the following fact, which we proved in the lecture on alternates. Any alternating polynomial, polynomial f can be written f. So x is in n variables, can be written, in fact can be uniquely written. So we didn't quite emphasize the uniquely bit when we proved this, but it's more or less clear from the proof and the same argument that we have used earlier to show that the monomial symmetric functions form a basis for the symmetric polynomials. Okay, can be uniquely written as a linear combination okay, now lambda varying over, well, just over n tuples. So let me just say lambda is weakly decreasing n tuple. Okay, and these constants vary over, are all integers in this case. Okay, so any alternating polynomial can be written in this form. This was the statement really, that the alternates are some sort of analogues of the monomial symmetric functions when we talk about the alternating polynomials. Okay, so now let's see why this is good for us. So observe further, if f is homogeneous of degree D, then we can say a little bit more. If f is homogeneous degree D, then all the terms that appear on the right hand side are also likewise. Then we conclude that all lambdas on RHS, in other words, i.e. those for which these constants are not zero, the coefficients, these must satisfy the following property, that the alternate must have degree D. So recall the degree of the alternate A lambda plus delta is mod lambda plus mod delta, okay, which is this guy. So this must be equal to D. Okay, now let's go back to what we are given, or what we needed to prove. We need to show that the Schur polynomials form a basis for the space of symmetric polynomials of degree d. So let's start there. So what does that mean? Given a symmetric polynomial in n variables of degree d, we need to try and express it in terms of the Schur polynomials. Okay. Now we'll do this as follows. We will instead consider f multiplied by, so f is actually a polynomial in the variables x, consider f multiplied by the van der Monde determinant, okay, or by the special alternate A delta. Now doing this converts it into an alternating polynomial, right? So we've gone from symmetric polynomials now to alternating polynomials. That's really going to be the key idea. We'll repeat this many times later on as well. So look at fx times A delta of x. This guy has the following properties. Number one, it's alternating. So what all do we know about this? This is alternating. Further, it's homogeneous of degree. Well, what's the degree? Well, it's degree d, that's f itself, and then A delta has degree n into n minus 1 by 2. So this guy in fact is homogeneous of degree d plus n into n minus 1 by 2. Okay. Now we use the fact that we just proved, okay, by what we just said above. Any alternating polynomial, in particular the polynomial f into A delta, can be uniquely expressed in terms of the alternates. This can be written as C, okay, where lambda varies over these guys, and then we are done, because all we have to do is just divide both sides by the A delta. This becomes summation. And those are the Schur polynomials. Okay, now lambda of course varies. Okay, good. So what does this show? This shows that any symmetric polynomial can be expressed as a linear combination of the Schur polynomials. But we also need to show that such an expression is unique, but the uniqueness now follows from the corresponding uniqueness statement for the alternating polynomials. Okay. So let me leave that bit again as an exercise. Show that these constants are unique as well. So prove uniqueness of such an expression. So f of x can be written like this. Exercise, prove uniqueness of the expression star. In other words, if there is another such way of writing it, then the two constants have to match. Okay, good. So that just comes from, like I said, from the corresponding statement about alternating polynomials. So the general moral of the story here is really this, that the Schur functions or the Schur polynomials are really defined in terms of the alternates. And so anytime you want to show something about Schur polynomials, what you often do is multiply everything in sight by the A delta, and thereby clearing the denominator of the Schur polynomials, and then it converts everything into a corresponding statement about alternating polynomials. Okay, good. So now two more facts which are important, or well, I should also say definition maybe. So we usually define the Schur polynomial as follows. Suppose I have a partition lambda of d, then we define it as follows. Given lambda any partition of d, we define S lambda in n variables as above, as A lambda plus delta by A delta in these n variables. If the number of variables, if the length of lambda, it's the number of non-zero parts, is at most the number of variables n. Okay, only then does it make sense to talk about A lambda plus delta and A delta. Okay. But so delta here is the n minus 1, n minus 2 till 0. Okay, so you can define it like this only if length of lambda is less than or equal to n, else we just set it to 0. Okay, so else S lambda of x1, x2, xn is just defined to be 0. That is, if the length of lambda is bigger than n. So this is a definition which extends the definition of Schur functions to all lambdas. Okay, if you have some fixed number of variables n, you can still talk about the Schur function S lambda for any partition lambda. Okay, if the number of parts of lambda is too large, then you just define it to be 0. Now this definition actually ensures that the following nice thing happens. This is sometimes what's called the stability property. For Schur functions, it says that if you take so this is true for any partition lambda. So it says given any partition lambda, say partition of D, Schur function S lambda in n variables x1, x2, xn, and then you set xn equal to 0. Okay, and just putting one of the variables to be the last variable to be 0, then this is the same as the Schur function in the n minus 1 variables x1 through xn minus 1. Okay, now this is in order for that to make sense, we should have extended the definition like this. That's the reason why I mentioned this this definition. So let's just quickly see why this is true. So observe that proof if length of lambda is, well, if it is greater than n, okay, is strictly greater than n, then it's clear that the left hand side, the Schur function, without even putting xn equal to 0, then of course the Schur function itself is 0. Then S lambda itself is 0, and of course also equal to the Schur function in n minus 1 variable. So this is also equal to the right hand side. So of course both sides are equal. Now if length of lambda equals n, okay, so maybe let's do this. If length of lambda is less than n, okay, or maybe equals n is a more important thing. So let's do equals n. So if length of lambda is equal to n, then let's see what happens to both sides. The right hand side is of course 0, because the length is n and there are only n minus 1 variables. So by definition, the Schur function in n minus 1 variables is 0. Now why is the left hand side 0? So observe that if length of lambda equals n, then what's S lambda evaluated at x1, x2, xn? This is nothing but a lambda plus delta in these variables divided by the Van der Monde determinant. Now observe what is a lambda plus delta. Okay, now what is lambda? Lambda, the length of lambda is n, right? So a lambda plus delta of x1, x2, xn is, if you wish, it's that determinant. And what do the terms look like in this matrix? It's x1 to the lambda 1 plus delta 1. So delta 1 is n minus 1. x1 to the lambda 2 plus delta 2 and so on. Now the last term is important. It's lambda n plus delta n, and delta n is a 0. Okay, now you keep doing this to all the terms. Importantly, look at what happens to the very last row. Lambda 1 plus delta 1, blah blah blah, xn. Okay, now the length of lambda is n, means that lambda n is positive, lambda n is not 0. Okay, in particular it means that all these guys, lambda n plus delta n is just lambda n plus a 0, but every term in the last row is actually divisible by xn. Okay, you can pull out an xn from every one of them. Okay, so in particular this means that if I set xn equal to 0, then the last row is just going to become identically 0. So observe, therefore this means that this is 0 at when I set xn to be 0, okay, keeping the remaining variables intact. So if I set xn 0, last row becomes identically 0, so determinant becomes 0. Okay, therefore the two sides match. So what does that mean? Therefore the Schur function S lambda at x1, x2, xn minus 1 and a 0 in the last component, that's just a 0. Okay, so therefore LHS and RHS are both 0 again in this case. So the only case which you really need to check is the one corresponding to length of lambda less than n. Okay, now what does that mean? If length of lambda is less than n, then it means that the lambda n is 0. So this means in particular that lambda n is 0. And now just look again at the same thing. Look at the Schur function S lambda at x1, x2, xn minus 1 and then set a 0 in the last component. Now see what this becomes. Again the same computation, a lambda plus delta divided by a delta. So we do that at this particular. Okay, now again let's look at what the numerator is. Now what is a lambda plus delta? So again it was that determinant, and let's again focus only on the last row where the xn's are. So this is xn power lambda 1 plus delta 1, xn power whatever lambda 2 plus delta 2 and so on. Okay, let's keep going till the last entry is xn power lambda n plus delta n. Okay, but both of them are actually 0 in this case because lambda n is known to be 0, delta n is of course 0. Okay, so this is xn power 0. Okay, and then of course I have some terms here in the rest of the matrix. So what's this matrix going to look like? Now I set xn to be 0, remember. So when I do that, all the other terms are 0 and this guy alone is a 1. Okay, and what I have here is this matrix with x1 power lambda 1 plus delta 1 which is n minus 1 blah blah blah, x1 power lambda n minus 1 plus 1 and so on. Okay, and this is the matrix whose determinant I am trying to compute, and so observe that the determinant of this matrix is actually, what is it? Well, that determinant is, since I only have a 1 in the last row, it's equal to the determinant of this submatrix, this n minus 1 cross n minus 1 submatrix, and observe that this is actually just the same as determinant of this submatrix, but that guy is the following. I observe that I can pull out x1 common from the first row. Okay, x1 is every element is divisible by x1. The second row, every element is divisible by x2 and so on. So actually you can pull out an x1, x2, xn minus 1 common by pulling out the appropriate variable from each component, and what's left, if you think hard, is actually just the same thing, a lambda truncated. Okay, so let me just put a bar on top, lambda truncated plus this is the delta for the n minus 1 variable, so I'll call it delta truncated with the n minus 1 variables x1, x2, xn minus 1. Okay, where lambda truncated just means I forget the last component, I think of it as an n minus 1 tuple, and delta truncated is just the delta version. I mean, this is not truncated in the true sense of the word, this is the delta for n minus 1. Okay, so delta bar will be, I replace n by n minus 1 everywhere. So this is delta bar. Okay, so sorry, slightly there's a mismatch of notation, so I'll call it delta hat maybe. Lambda bar is just the truncation, delta hat is not the truncation of delta, it is the delta vector corresponding to n minus 1 rather than n. Okay, now what does that mean? It just says that this determinant is this particular expression here, and now we just have to see how a delta behaves. So now observe what is a delta of x1, x2, xn minus 1 with a 0 in the last component. We already know what this product is, it's xi minus xj, I less than j. And observe, if you put xn equal to 0, then there will be terms of the form x1 minus xn, x2 minus xn, and so on. All of them will just become x1, x2, x3, etc. So observe again, there's an x1, x2, xn minus 1 which comes out common, and what's left is exactly a of delta hat evaluated in the n minus 1 variables x1, x2, xn minus 1. Okay, and now you can see how the proof works, because now what we did is to say, if I take s lambda, then it was a lambda plus delta of those variables by a delta of those variables, but each of them has a common factor x1, x2, xn minus 1. And what's left in this case is a lambda truncation plus delta hat in fewer variables. Okay, and again x1, x2, xn minus 1, which you cancel, and if you sort of really think about what you have here, that's exactly the Schur function s lambda again in the n minus 1 variables x1, x2, xn minus 1. Okay, observe the last component of lambda was a 0, right? So when I want to think of s lambda as representing as indexing a Schur function in n minus 1 variables, I only take the first n minus 1 components of lambda. Okay, good. So this is the stability property of Schur functions. Okay, and so it's a important observation somehow. Okay.